This is Yufei from Snowflake. I'm a PMC member of the Apache Iceberg and Apache Polaris. Ethan, you want to give a brief introduction?
Yeah, I'm Ethan. I'm a data infra engineer at Onehouse, and I'm a Apache Hudi PMC member. I drive key initiatives around data lakehouse in Apache Hudi project.
Thanks, Ethan. So today we're going to talk about the Polaris meet Hudi, unifying the lakehouse metadata clause table format. And this is what we're going to cover. First, I'm going to talk about what is Apache Polaris, why do we need that one, how does it work. Then Ethan is going to talk about new concept within the Polaris, which is generic table, and how does support the Hudi table format. A few years ago, I was working in a big tech company. We are using a lot of the Iceberg tables with Hive Metastore. And this one Friday afternoon, we get a ping by our users. Something happens to their tables like this. It's kind of a horrible situation because once you see this, actually your table has been corrupted and nothing can happen to that table, no read and no writes. All these pipelines had to stop. And even worse, like we don't know what happens. It could be server-side issues. For example, there's latency issue from server side that caused the lock to release prematurely, or the client side, the client did not handle certain exception well. And we spent a lot of time to finally restore the table, and it's very crashing weekends, and we don't want that happen again. So what happened to right now is a lot of people use Iceberg, still use these traditional Iceberg, traditional catalogs, Hive Metastore or JDBC catalogs. And for people who don't know Iceberg very well, these there's two layers, metadata layer and data layers. In the 3 layer of the metadata, the top layer is the metadata JSON file, or called a version file, which hold all these schemas, properties, partition spec, and at one point to the manifest file for the snapshot. The manifest list file is the one hold all these, it basically represents one snapshot and have the file path to manifest file. And the manifest file layers has all these file paths to the data files and hold all these status of the min-max for columns. So what catalog does here is has one file path pointing to the metadata JSON file, the top level metadata file. And every time you do a commit, you have to lock that table. And then you finish your commits, then you unlock that. Anything happen between the lock and unlocks could be a disaster, right? Then you potentially corrupt your table. And because metadata JSON file is the one file stored in your object storage, there's potentially like each individual engine and workloads have to pick them up from the storage, and the IO cost is really costly. So there's no caching happens for that one. Even more concerning is the compatibility issues, right? If you have old client, let's say you have Spark 3.2, 3.4, 3.5, and Spark 4.0 with different Iceberg versions, and these new Iceberg versions has some property that old client does not know that at all. And every time the old client writes the metadata JSON file, right, then it will override that one, and which causes the table to corrupt again. Okay, looks like we need a better catalog. But before we dive into the better catalogs, I want to briefly introduce a little bit about Iceberg commit model. We call it optimistic concurrency. So for each Iceberg table, we can have multiple versions. Every time we make change to the Iceberg table, this new version has been generated. And to commit that version or work on one version, we don't lock that table, right? Client 1, for example, here, client 1 pick up version 1 and then make some change to commit as version 2. And then client 2 pick up version 2, make some change and commit as version 3. But both of them, they don't have to block each other. This is happy path. As you may know, that it could happen in concurrency. When you have concurrent writing to the one table and both client 1 and client 2 pick up the version 1 of that table and try to make some change and commit, but only client 1 succeed. Client 2 find out the base has changed. What happened to client 2 is it had to fall back. It will fail, v2 prime will fail, fall back, do conflict resolution, and commit as a new version, v3. Hopefully that goes through. So the whole conflict resolution is very costly. We should prevent it early, and we should resolve it better. So it's nature come to these requirements for nice catalogs. If we can have reliable and low latency commits, then fast commits usually means less conflicts, right? If you look at the optimistic concurrency model. And still, conflicts inevitable sometimes. We need a better conflict resolution to avoid these back and forth between the client and the server, as well as the client itself has to do some conflict resolution. And not only all about Spark and Spark or all these computation engines, there's huge amount of the ecosystem within the data analytics area. They want to hook to these catalogs and check their metadata data for their table. So easy client implementation was also preferable. Last but not least, data governance is also very critical for the enterprise user. So a few years ago, the Iceberg community started working on one thing called Iceberg REST catalog, spec. And it did one thing, it looks like very simple. So if you look at these orange bar, which is the catalogs, right now we shift the responsibility of the client to write this metadata file to the catalog writing them instead. It looks like very simple idea, but I'm going to show you this simple idea will change the way we use Iceberg table completely. So with REST catalogs, we shift the client responsibility to the server side. So server side handles all these commit and retry. There's no table lock, and you don't have to run the table before you commit. And the faster is more reliable. And because server writes metadata file, it is also change-based. If you do the DDL, you don't have to send all these snapshot history back to the server, and you just send the specific change to the server. So it has reduced the compatibility issue significantly. The server usually know better context of how it resolves conflicts. So it improves the decision-making and the commit time. For example, when you have DDL versus DML, you don't have to fail one of the commits if they are compatible. It's server just do it again. Server just consolidate them and commit as a new commit. So it saves a lot of the back and forth between the client and server. And even better, when you have, for example, compaction commits versus ingestion commits, we usually want to prioritize ingestion commits. And you can say, okay, if ingest base has been changed, we just roll back the compaction and we can do compaction later. Always let the ingestion commits come into your table version history. And for use case like multi-table transaction, it's only possible when you have the IRC that you can send a bunch of table commits within one request, and the table we can sort them as the transaction. Also, when we shift all this responsibility from the client to the server, it's encouraging more clients, like Python, Iceberg, and Rust. Some of the new clients in the very beginning, they only develop against IRC. Over the years, we also developed a bunch of the new features within the IRC. We provide view support. It's not that original. We provide ETAG, which is to improve the efficiency of the load table. And then we provide server capability, which clients can understand what kind of the endpoint server has. Credential refreshing is critical for long-running jobs. They want to refresh their credentials over time. And item key is to improve the reliability of the retry. And the server-side planning is a very big feature that the catalogs actually extend a little bit to the manifest file. There's a bunch of exciting new features we're also working on, like event endpoints, UDF. Other than table view, we try to put the UDF into the catalog so that they can be shared across multiple engines. FGAC is another big push. And we try to use the read restriction along with load table so that the trust client can be applies FGAC policy into the table. So with so many great features within the IRC, Iceberg community have decided not to provide a reference implementation. So that's how Apache Polaris coming into the picture, this product was developed about 2 years ago by Snowflake and donated to the ASF. About 3 months ago, Apache Polaris has been graduated to the top level Apache product. So as long as all these engines are compatible with the IRC spec, it can work with Polaris seamlessly, no matter it's your favorite open source engine like Spark, Flink, and Trainer, or any proprietary engine you try to use. As long as they're compatible, it can work seamlessly. And Polaris support all these great features for IRC. We are almost the best feature compatible catalog there. Table view and support native OAuth 2.0, multi-table transaction, the conference resolution I just mentioned, e-tags, credential vending, all these features are supported. So one of the great features for Polaris is the credential vending. Before credential vending, what you have to do is to configure, like for example, if you let your workflow to read and write your files in your storage, like the S3 or Azure, you have to configure all these sorted credential for each individual workflow. That's a lot of job. And even worse, because right now you have 2 places for the access control, where one is from storage level, another from catalogs. So Apache Polaris provides the credential feature that workload does not have to configure that one. The catalogs were vending them, combined with the native RBAC capability of Polaris. So you have this one centralized place to manage all these access controls. For example, you have the user, and it only has read privilege, and it will only get read privilege for their its Iceberg table or any other table. And Polaris is developed as the micro service architecture, so it can run any Dockers, Kubernetes, any cloud providers. Kubernetes offers the EKS, AKS, for example. Here's the commit roadmaps. And on the left side, it's the things we've already done. On the right side is what we are working on. We've already provided data support, IRC, federation, a bunch of new governance features has been adding to the Polaris, even external PDP like Ranger support and OPA support. We are also working on very exciting new feature like RBAC. Sorry, not RBAC, the FGACs, row column level access control, taggings, data lineage. And one of the big thing is Polaris also support non-Iceberg table, that we have a new concept called the generic table, and it can support all kinds of data table format. Let me invite Ethan to talk a little bit more about the generic table and the Hudi support. Ethan.
Yeah. Thank you, Yufei. So next, I'll talk about how Polaris expands support beyond Iceberg. And when we look at how data actually sits on storage, as you can see here on this slide, the fundamentals of these different lakehouse formats, including Hudi, Delta Lake, and Iceberg, are actually pretty similar. So each format creates a specialized metadata layer on top of raw data stored in Parquet files. So if you look at this, for example, for Hudi, it stores the table metadata under the .hudi folder. Similarly, Delta Lake uses its transaction log, and Iceberg uses Avro-based metadata files. So the key takeaway here is that these structures are format specific, but share a common goal. So it points the engine to the right Parquet files. And this architecture is consistent whether you are running on Amazon S3, Google Cloud, or Azure data lake storage. So because these layouts are standardized, Polaris can act as a unified management layer without forcing you to change how your data is physically organized. So let's move on to the next slide. So you may wonder what Apache Hudi is. So for some of you who are not very familiar, Hudi is more than just a table format. It is an embedded headless distributed database built specifically on the cloud storage in this era. So let's break those terms down. So embedded means that engines like Spark, Ray, Flink act as a stateless client. So they handle the heavy lifting of reads, writes, and table maintenance. Headless means there are no central storage servers to manage or scale. And distributed means the system scales horizontally by interacting directly with the cloud storage. So Hudi essentially splits itself into two parts. So on the one hand, you have the storage engine, which manages byting logic, concurrency control, and record level indexes, for example. On the other hand, as you can see on this diagram on the right side, you have the storage format on the bottom, which handles the schema, file listing, column stats. So this dual layer approach allows Hudi to support everything from incremental ETL jobs, which can provide really low latency on the right side, and also low latency interactive queries. So if we move on to the next slide, Hudi is now evolving into AI native lakehouse as well. And we are adding support for the need of modern large language models and AI workloads. So we are introducing native vector type for vector embeddings directly in your tables. We are also adding vector search SQL, as you can see here, so that you can do similarity searches using standard SQL command. We are also adding native blob type for unstructured data like images and video files, and lens file format support, as you just heard from the previous talk about lens, which is optimized for high performance and access patterns. And finally, we also have native variant type support for flexible and semi-structured data. So if some of these AI capabilities caught your eye, I highly recommend catching a talk later today on Apache Hudi for the next generation of AI, unstructured data, and vector search. So there's some interesting thing happening in Hudi. So now going back to Polaris, if you move on to the next slide, Yufei. So we want so users on Hudi and to use all these features and also like can benefit from Polaris catalog, which is now growing like a single or unified management for tables. So this brings us to like a major challenge in the ecosystem. As you can imagine that the Iceberg REST catalog specification is currently gold standard in Polaris, but it was not designed specifically for is especially for Iceberg, but it's not specific for other formats like Apache Hudi and Delta Lake. So to solve this, Polaris introduced this specification or concept called generic tables. So this is a critical bridge. It provides a standard set of REST endpoints, as you can see on this slide, get, post, and delete that allow Polaris to manage non-Iceberg tables. And if you look at the JSON schema, you see how simple the representation is. So we can define any table by its name, its format. And in this case, we want to support Hudi, then it should be Hudi. And also the table-based location. So by using these generic table APIs, Polaris can finally offer a single unified catalog for every format in your lakehouse.
Nice.
So
I wanna jump in real quick. Sorry, guys, and let everybody know this is technically Q&A session now. So if anybody has questions, I already see there's one question for you guys already. So please submit those, like the ones that you'd like to see on the screen, but I'll give you guys a few more seconds to wrap up.
Okay, so have like a few more, like maybe a couple minutes to wrap this up. So just to talk about like how we support Hudi in Polaris. So basically, we give the first class Hudi support within Polaris 1.3 release, and kudos to Rahil who added this implementation. Basically, particularly, Polaris provides like a specialized Spark client that perform read and write operations on these generic tables. And then it helps to basically generate Hudi specific metadata directly from cloud storage. And if you move on to the next slide, which is the last one. So this shows how it actually works. So it's a joint integration with mutual catalog delegation between Polaris and Hudi. So all this starts with user running like a standard create table command in Spark SQL using Hudi format. And then Hudi catalog receives this request and then delegates to Polaris for creating a table. So now all of these can happen in the same way, so that for this Hudi table is fully discoverable and governed by Polaris. And you also have a single catalog for governance across Iceberg, Delta Lake, and Hudi. So it's really about centralizing your data lake without actually forcing it to migrate all your data to a single format. So that's all about this talk, and going back to Yufei for wrapping this up.
Thanks, Ethan. Yeah, the last page is the Git report, and Polaris is very new project, and I welcome all these contributions. We are open for questions.
Awesome. Yufei, Ethan, thank you very much, guys. This was excellent. We have one, I'll put it up on the stage. What capabilities exist or lack between generic versus the Iceberg catalog for query engines?
Yeah, we are actually working on one of the big features for generic table, which is support the credential vending for generic table. It is already there for the Iceberg table. And when it's available, then it will apply to all these the other table format like data Hudi or other table format. I think so. Another question I can answer: the server-side scanning is working in process.
This one, okay, yeah, we can, yeah, go for it. If you're seeing that, right. Another one in the chat. So, yeah.
Right. We are working on the server-side planning. It's not there yet, but we're working on that.
Nice. So coming along. Nice. And you want to stick around in the chat for a bit longer, and also put maybe the QR code or a link in the chat too for the folks that are that had not gotten a chance to see that QR code for how to contribute to the Polaris Git repo. Thank you very much, guys. I appreciate you coming.
Thank you, everyone. Thank you, Adam. Thank you, Yufei.
Thank you.
Thank you, Adam. Thank you, Yufei. Thank you, everyone.
Thanks, guys. Okay.